We're going through some examples of what the pipeline looks like, what its design philosophy is, and how it works. The kind of the thing we've been trying to keep in mind throughout all of our development, and that you should try to keep in mind this morning as well, is this philosophy I've got on the upper left hand there. So the web pipeline will never automate everything for everybody, but our aim is that it should be capable of doing most things for most people. And what that means is that there'll often be things that you want to tweak about the pipeline in order to do the best possible job for your science case. You should have most of the tools that you need available within it. So give you an idea where I'll be going today. First half of while I'm talking to you, then I'm going to give you a background on what the pipeline is, how it's broken down into various different stages, what kinds of data products it produces, how we go about doing our development internally, and then kind of segue from that into how do you install the pipeline, how do you run the pipeline notebooks, leading us into that live notebook demo using the webinar platform that we'll be using today. After we finish actually working with the notebooks themselves, then I'll wrap up with a bit more information for you about kind of where to go from here. Information about how to find documentation about the pipeline, some of the things you might want to keep in mind when looking through the data, things that you want to tweak about the pipeline, and give you an idea to how to stay tuned in terms of the things that we're changing about the pipeline over time, and other things you can use to take the information from today and start using it to do science with your own data. So to give you a bit of scope behind it, the web pipeline is a single pipeline for all instruments and all modes on JWST. So that's, depending exactly how you count it, roughly 17 different kinds of modes, broken down into a large number of both imaging types and spectroscopic observations as well. For standard imaging mode observations, then there's classic imaging, a large detector taking imaging observations in multiple filters of a given field. Has coronagraphic observations, where you blot out the light from some central source so that you can look for faint stuff nearby. Aperture masking interferometry, and time series observations, where you look to see how things change over time so you can detect small time-dependent signals in a given object. It's got a wide number of spectroscopic modes as well, ranging from traditional slit-type spectroscopy all the way through multi-object, wide-field slitless, and even integral field unit spectroscopy. So the web pipeline handles all of these things, although it splits off into various different submodes according to what exact kind of data you're trying to process. It also has to handle the kind of science data from a wide range of programs, all of which have their own. So some of the different concerns that you have range depending on what kind of science objects you're looking at. If you're looking at bright solar system targets, then you have one set of concerns. Here's an example, for instance, of some really beautiful observations that the MIRI-MOS integral field unit spectrometer took of the giant planet Saturn recently, for instance, where you can see these squares here and over here on the rings are actually images created from collapsing the IFU cube data into single images from the spectroscopy. That means that we now have spectroscopy across all of these regions as well, where you can see these super rich, very deep molecular features all throughout the spectrum. So the concerns you would have here range from things you get orders of magnitude difference in brightness from near saturation at the top to very faint on very short distances in terms of wavelength space. That gives you one range of concerns that you'd be interested in the pipeline. Range from that to looking at exoplanets, where you don't necessarily care all that much about exactly what your flux calibration is, but you care a lot about the stability of the system so that you can try and pick out few parts per million or so and detect things like water vapor features in planets around other stars. And all the way from that to galaxies and cosmology, where we're always pushing the edge in terms of the highest redshift sources we can detect, the faintest PAH-type features in galaxies, where you really care a lot about what's going on at the detector level and need to correct for all of those artifacts in order to push the boundaries of what we understand about objects in the very distant universe. Here's how the pipeline itself breaks down. There's kind of two parts to the pipeline. The first one is the pipeline code itself. As I mentioned, that's a shared pipeline code across all different instruments, all science cases, etc. I put a lot of links in this presentation, and not necessarily that you'll follow them now, but you can download this presentation later and follow those links and explore this on your own time. The link to the pipeline code itself is here at the top. It's publicly available on GitHub and available for anybody to read and contribute to if they want. The documentation I'll touch more on later, but here's the link to it in one place. There's some dependencies we have on various other packages as well. It's developed in a almost entirely Python-type environment. So there's the JWST Python package, and it depends on a variety of other packages that are produced and managed by Space Telescope as well. Some of those include things like the Drizzle package, and also broader astronomy community things such as AstroPy, NumPy, SciPy, and various other common packages. As I said, it's mostly Python, but it does have some C bindings we've implemented in there for speed. What that means is when you install it, then those C codes will need to be compiled, so you will need to have a compiler active on your computer. This makes a really big difference in some steps for the pipeline. So some of the changes we've made in the last year, for instance, pushed some of our longest running Python steps that could, in some cases, take over an hour for a given observation, and pushing those over to C has now made them run in less than a minute instead, which is much more tractable for people who are trying to run the pipeline at home. It's also been designed to be very highly modular so that you can skip, modify steps, or actually even add steps as you want, depending on what you want to process for your own data. And finally, we support this for both Mac OS and Linux. Windows, unfortunately, isn't supported at the moment, mainly because of issues to do with those compilers being a little challenging to work with on Windows operating systems. And the second side of the pipeline, we had the software side first. The second side is the reference files. These are all of the calibration reference files necessary in order to actually process the data. So things like our dark reference files that tells us what the typical dark current of the detectors is, things like our flat fields, our photometric calibrations, all of those pieces of reference data necessary to turn raw data we get off the telescope into calibrated science data that we need to actually do our various science analyses. So many different pipeline steps rely on these reference files, and it will retrieve them automatically as needed. In case you want to go see the files themselves, then there's a link here to where you can find them on the CRDS, or the Calibration Reference Data System server. And how the pipeline works now is that each pipeline version you run corresponds to a fixed set of reference files. So if you run, say, the build 11.2 pipeline, you will get the build 11.2 reference files that are designed to go with it. We release new versions of the pipeline regularly and new versions of the reference files that go along with that pipeline as well. And finally, the pipeline notebooks I've linked to at the bottom put this together. And that's how you actually can get an idea of how to run the pipeline. It'll show you how to run the pipeline code. It'll automatically use the reference files. So this is kind of where you get started at the bottom in terms of running both of the above. And that's what we'll walk through a bit today. Jumping into a bit more detail in terms of how the pipeline itself actually works, though, it's broken down, as I said, into various different stages, with the idea that depending on what you want to do or change about the pipeline, you might only need to rerun one or two stages of these. You don't always need to start from the raw data off of the telescope and go all the way through to the other end. There's multiple intermediate stops in the middle, and you can choose which ones you're interested in trying to look at, tweak, and modify to see how it can benefit your own science data. Where we start is up here at the top. This is so-called stage 0. This is the uncalibrated data. It's been downloaded from the spacecraft via the Deep Space Network, and we've packaged all of that telemetry into a convenient format. So these are the so-called uncal.fits files, which is the raw data that we get from the telescope prior to really having any processing done on them. After that, there's 3 stages to the pipeline. The first one, creatively called stage 1, is the detector 1 pipeline. And here's where we deal with all sorts of detector effects. So we take those uncalibrated files and we deal with fitting slopes to the ramps, which I'll explain in a moment exactly what that means. And we give you some kind of a output image that you can look at and see, roughly, after removing detector effects, what does the image of your scene look like? Second part is stage 2. Here's where we start to specialize a little bit depending on what kind of object or what kind of data you're taking. There's both a imaging and a spectroscopic pipeline. The idea behind both of them is that here's where you start to do the more astrophysical calibrations. You figure out what the coordinate mapping is, what the wavelength solutions are. You do your flat fielding and your flux calibration. So at the end of that, then you get actually calibrated images. So in units, say, of megajanskis per steradian, some physical, meaningful flux unit at meaningful locations on the sky and wavelengths. So this is where you can start to do science with the data. Then finally, this last stage of the pipeline is where it gets really specialized according to mode. So there's an imaging pipeline, a time series pipeline, a chronographic pipeline, etc. And here's where you try and combine together multiple images. So this is your traditional co-adding data, averaging data together, making final spectroscopic data products, etc. And everything in these intermediate stages and this final stage here all goes into the MAST archive so that you can download it and look at it yourself. So with that overview, I'm going to try and step through a little bit what each of these individual pieces are and why we run them. So if you look at uncalibrated data, the data that we actually get off of the spacecraft, it's actually four-dimensional, which takes a little bit of time to kind of wrap your head around what that means. But the easy way to think of it is that you can imagine that the Webb detectors are two-dimensional detectors. They're somewhat similar to the detectors that you have in digital cameras. They're a different kind of technology, but they give a two-dimensional readout. You've got rows of pixels, X and Y, and it gives some image that it's recording from the telescope. So that's two dimensions, X and Y on the detector. And also, because of how these detectors work in the mid and near infrared, you don't just read them out one time and you're done. You can actually read them out non-destructively, meaning you can read them once, wait a bit of time to collect more photons, read them again, and you can keep doing that and build up signal over time. So you actually get measurements that kind of go up a ramp like this, where this is the first group you read in which, well, it's time equals 0. There isn't all that much signal from your object that you're looking at there. And then you read it multiple times until you reach some higher part on the ramp. Say you've been integrating for 5 minutes or so, reading every 20 seconds. That gives you a good sampling of the data that you can use to reconstruct what the scene itself actually looks like. And then you can take multiple of those ramps. So the 4 dimensions that we're working with is X and Y detector image, the number of groups up this ramp, and then the number of integrations. How many different times did you read up the ramp? So if you want to know more about this, I provided a link in there that you can use to understand kind of how this data is structured. But the benefits of doing things that way is it allows us to calibrate the data a lot more easily. So for instance, the slope, the ramp I showed you here was nice and smooth. It went all up as a straight line until the top, you reset it, and then you did the exact same thing again. That's not what you see in real data. Instead, you start seeing things like this. We're up in space. It's a very harsh radiation environment. We're getting zapped by things like cosmic rays constantly, and that will break up this ramp. So you were reading a given pixel up the ramp, getting slightly more signal each time as you accumulate more photons. And then you get hit by a cosmic ray, and it jumps up here. But no, after that, you keep accumulating data from your source in about the same kind of a way. And if you only read the data once, so you had a 0 point and an end point, you'd get some biased slope that tried to connect the first and the last points of this line. As it is, because we have all these reads in the middle, then we can find the cosmic ray. We can say, hey, this gap here was affected by a cosmic ray. There's a big jump. So let's ignore that when we fit the slope. And when we fit the slope to this data to find what the rate of counts from our source of interest is, we can get a pretty good measurement because we can cut these cosmic rays out of our calculation. Likewise, it gives us a bit more dynamic range as well. So here, for instance, you can imagine getting up to saturation fairly quickly on a very bright source. So say you saturate on that bright source in just a minute. The information is not lost. We can build our slope for how bright that source is just based on the groups that we had here before we hit saturation. But we can let the detector keep on integrating for 5 minutes, 10 minutes, 15 minutes, etc., so that we can get more dynamic range. We can get these longer ramps on faint areas, even if we need to cut them short in processing for very bright objects. So this is kind of the motivation behind the way that we read out the detectors, and a large part of what the first stage of the pipeline is designed to deal with. It takes these kinds of ramps, and it turns it into the images that you're more familiar with working with. In detail, for the folks who are interested, here's a breakdown of some of the steps that happen in the Detector 1 pipeline. I'm not going to go through all of them. There's a lot, but they cover various different things you might need to worry about. For instance, in the mid-infrared detectors, you're worried about electromagnetic interference from the cooler system on JWST. In the near-infrared, then you have corrections that you need to make for the super bias or the 0-point level of detectors you're starting at. You worry about the dark current, the rate at which counts in the detector go up just by thermal issues with the detectors themselves. You look for cosmic rays. You can correct for 1/f noise, which I'll go into a little bit more later. And then kind of the final step at the end is where you fit this slope, and you get an image for the detector. So to make that a bit more intuitive for you, here's just an example for a very simple imaging case. So this is a near-cam imaging observation. On the left, I'm showing you a single frame of this so-called uncal.fits file, the starting point that we get off of the spacecraft. And it looks kind of like a mess. There's all sorts of blotchy structure over it. You can see, maybe a couple bright things, which are your very bright sources. You've got lots of individual white spots from cosmic rays in there. It's hard to really see what you're looking at. And when you finish processing things through this detector 1 stage, you get something that looks like this on the right instead. You've subtracted out all of these 0-point differences between your different pixels. Now you're just fitting the slopes, you're eliminating the cosmic rays, and you end up with something that looks a lot more like an image of a scene that you might be familiar with. It's still not perfect. You can see there's all sorts of weird illumination patterns, but that's something we take care of in the next step of the pipeline. This next step of the pipeline is the either image 2 or spec 2 pipeline, depending on whether you're processing imaging or spectroscopic data. And the purpose of this part of the pipeline is to take those images coming in from the first stage that were in some physical units of data numbers per second. They're physical in terms of what the detector recorded, but they're not meaningful in a scientific sense. And produce calibrated detector images in terms of something that's actually radiometric, Jansky's, steradians, arcseconds, etc. There's a variety of different steps in here. Again, I'm not going to go through all of them in detail, but just give you an idea about some of the things that this step involves. Image 2 is fairly straightforward. The first thing is that it goes through a step where it associates each pixel with our model of the telescope distortion, the instrument distortion, and where the telescope was actually pointing on the sky, so that you can say pixel 519,320 was at this RA and this deck. That gives you the information necessary to find yourself in space. You can correct for various other artifacts like the flat field correction, how responsive is each pixel on the detector to incoming light. And you can apply a flux calibration. We've spent a bunch of time looking at standard stars, so stars whose brightness we understand very well, so that we can turn these data numbers on the detector into actual radiometric units whose measurements we can use to do science with. On the spec 2 side, things are obviously a lot more complicated with many different stages, but it's the same kind of idea. You start with figuring out which pixel maps where on the sky, now both in terms of rate ascension declination and also the wavelength of a given pixel as well. You can make flat field corrections, you can subtract off stray light that might be coming from various sources in the detector, and you end up with a flux calibration before providing some final product. Again, taking the simplified example of near-cam imaging, here's what the difference looks like before and after this stage. On the left is this image of the sky that we got coming out of the detector 1 pipeline. You can actually tell it's observations of galaxies and stars at this point, but it's still got these weird illumination patterns. That illumination pattern gets taken out by the flat fielding that we did in the image 2 stage, and now you have something that looks like this instead, where it looks a lot closer to something you might actually want to do with science, and you could actually say, for this galaxy here, here's the RA and deck associated with that observation. And kind of the final stage of the pipeline is this stage 3 pipeline. And here's where we start to split off, as in the figure earlier, to many different kinds of pipelines for different observing modes. So you want to do one thing for standard imaging observations, one thing for coronagraphic, a different thing for time series, etc. And I'm not going to show you breakdowns of all the steps in each one, because otherwise this webinar would take a very long time to go through. But the idea behind all of these is very similar. The idea is here you start to combine together multiple different exposures in order to create some final science quality data output. So if you've dithered around your observations on a given source, for instance, Here's where you co-add all of that data together, you rectify it to some common frame, and you produce the output files that we're used to working with to do our various different science analyses. So this might be drizzled imaging mosaics, it might be IFU data cubes, it might be time series observation light curves, or PSF subtracted chronographic observations, etc. This is achieved by something called an association file, which links together all the different input files. I'll talk a bit more about this later, but this is how we link together all of the files that need to be combined together into these final pipeline products. And again, I'll give you an example of what that looks like here. Here's what we just saw after the image 2 pipeline for some NeoCam imaging, showing you the calibrated data for a single exposure. Now on the right, I'm showing you the output of the image 3 pipeline for the same kind of a thing. This is a different kind of file. It's now called an I2D file, meaning it's an imaging file that's been rectified in 2 dimensions and combined together. And you can see that the noise properties of this are now much better. So around the edge of things, then it's still pretty noisy because we don't have as many observations. But in the center of the mosaic, where all of your dithers and your pattern overlap, you now see that the image quality is a lot better. You've managed to go a lot deeper. And this is the kind of data that we're used to using when we do analyses of our favorite stars, our favorite galaxies, or whatnot. And it's these kinds of products that are produced by the stage 3 pipeline, whether that be for simple imaging, whether it be for IFU spectroscopy, or any other kind of a thing. When you actually download data from the web pipeline, then you'll see file names that look like some giant long string of numbers and letters that can take a little while to get used to. Those giant long strings are actually very meaningful, and you can get a lot of information from them once you know what it is you're trying to look for. So I put one example here in from one of our MIRI MRS observations and tried to sort of color code this by the information that you can pull out of one of these strings of files. The first one's easy. JW just tells you this is JWST data, which you probably already knew since you went and downloaded it. The next set of numbers is telling you what the program ID is. So if you've got your own JWST observing program, you applied for time, you were awarded time, you were given a given program ID to do with it, this is how you identify which data is associated with your program. It's this next set of numbers. Within a given program, things are broken down into individual observations. Let's say you had 10 of your favorite stars you wanted to look at. Each one probably had their own observation number. These yellow numbers here will be how you find out which observation number it was, observation 3 in this case. It gets a little bit more obscure for a while after that point. The green numbers is a so-called visit number. This is relevant if you've got a very big program that has a single observation that's dithering around and it needs to do so in multiple different passes for the telescope. So this would be the visit number. For most people, it'll only ever be 1, but it can change for very large programs. This light blue number here is the so-called activity number. So if you're doing a big observation with lots of parallel imaging in different instruments, here's how you can kind of distinguish different parts of that. And then we get into pieces that you're more going to be using again. This dark blue number here is the exposure number in the sequence. If, say, you took a 4-point dither, then this number will go from 1 through 4. If you took a set of 57 dithers, it'll go from 1 through 57. Here's how you see what the exposure number is. And then finally, these last sets of things. This purple name here will tell you what kind of data you're working with. In this case, it's from the MIRI integral field unit spectrometer and the long wavelength channel. It might be the NeoCam imager, the NIRIS imager, whatever. That'll be telling you about what kind of data it is. So I told you about the different pipeline stages all the way from the uncalibrated data. The detector 1 pipeline makes these rate files. The image or spec2 pipeline makes cal files, and then the final pipeline makes I2D and other kinds of files. This is how you see what stage of the pipeline is finished. So I could tell you just by looking at this file name that it is MIRI IFU data, long wavelength channel. It's just finished the detector 1 pipeline, this program ID, observation number, and exposure number. So I don't need to even open the file. I can already tell most of the information I need to know in terms of what I want to do with it just by looking at the file name. Things change a little bit as you look at the final data products coming out of the end stage of the pipeline. As I mentioned, stage 3 combines together data from many different exposures. So this kind of numbering scheme doesn't make sense because there's many different things that fed into it. But it's the same kind of idea where you can get lots of information from the individual parts. Again, there's something that tells you about the program number, something that tells you about the observation number. There's a couple different kinds of associations I won't go into here, but now these numbers here tell you about what part of the program it started from. And then this string here tells you information about what kind of program it is. In this case, it was MIRI imaging using the sub-64 subarray and filter 18 microns. And likewise, I2D tells me that it's come out of the final stage of the pipeline, is resampled and drizzled, combines together multiple different images. So this is the kind of thing that I imagine it's lots of information to absorb right now, but certainly later you can look back at this if you wonder, what does that great big long string mean? And try and learn what the different digits mean in terms of understanding when you see them in your own data. The data product format, the things that we're providing, I've been using the phrase FITS lots of times, which I assume most people on this call probably understand what a FITS file is. It's a special kind of a data file designed a while ago now for storing astronomy data, where you can put lots of different pieces of information into the same file. And there's three pieces that are most relevant to folks when we're doing our science analyses with the data. And these are these three extensions or sets of data in the file. There's the psi, error, and DQ arrays. So the psi or science array is the one that's perhaps a little bit more obvious, and that actually contains the science data. I looked at this part of the sky. Here's the image that I got in whatever calibrated or uncalibrated units are appropriate for that stage of data processing. The error array gives the uncertainty in those observations. Uncertainty is always pretty tricky to estimate. There's a lot of terms that feed into that, but the pipeline provides our best guess of what an estimated uncertainty is associated with each one of these science arrays. So if you have a 2D image of a field with a science array, you'll have a 2D image of the error map. If you have a three-dimensional IFU data cube, you'll have a three-dimensional error data cube as well. And then this third one is the DQ array. That's the data quality array. And it's a bitmap that tells you information about that pixel. The most important thing it tells you is, should I use this pixel or not? It's got lots of other information as well, like I found a cosmic ray or the flat field isn't great, and most of those you can kind of ignore. The main one to pay attention to is this data bad? Should I use it? And that's just an odd number thing. If the number you find in the data quality array is odd, you shouldn't use it. And we try to make that really obvious as well in terms of how we present the science and error information. Anywhere that the data quality array is set to the creatively named do not use, we also set the science array to nan, or not a number. So there is no number there at this stage of the pipeline. One of the reasons that's useful is because if you're looking at a final 3D image file from a given set of observations, it tells you where you don't have information. So this is an image of the MIRI footprint, for instance. This is the MIRI imaging detector. There's this large rectangular field out here that actually sees sky. There's a smaller square field here, which is our LEO coronagraph, which mostly sees sky, except for this LEO bar going through the middle with an occulting spot that's designed to block out bright sources. And then all of this stuff in through here is places where we don't have information through sky, at least not that you'd want to use for imaging purposes. So it's really obvious to tell when you look at this calibrated data. It's now been flux calibrated. It might have been rectified onto some output grid that matches the sky. You can see where we have data and where we don't. And that means that if your object was here, you have no information, so you can't measure anything from that. Likewise, if you had saturation, say, if we saturated the middle of this star here, that might also be given these nan-type values to say, hey, I don't know exactly how bright this is, so you shouldn't be doing science with these values. There's some ways to work around that, but it's indicative of where you should and should not trust the data. In this particular example, I've just color-coded everything that is not a number in red because it stands out really obviously. But you're, of course, welcome to color-code it whatever way you see fit for whatever's useful for you. In terms of the development that we've been doing on the pipeline, generally we follow a quarterly development schedule, meaning that we put out new pipeline versions about 4 times a year or so. We're starting to transition more to sort of 3-ish to 4 times a year, but roughly every 3 to 4 months, and you'll be able to see a new version of the pipeline, updated reference files, and things that should do a better job of processing your data. We do recommend keeping up with what the latest version of the pipeline is so that you get both the latest calibrations, the latest software suite, and etc. So here's how we kind of break down our own development into different versions and the life cycle that a given software build goes through. Here I'm calling a build both a released and tagged set of the JWST calibration software, but there's also a large stack of Python type dependencies and reference files and everything else that goes with it as well. So a given build that we're working on starts off as a development build. Here's what I've color-coded in yellow. This is what we're actively working on at any given time. It's changing daily, and while you are perfectly welcome to use it if you want to, you can download it from GitHub, we really don't recommend it in the sense that it might not be working on every given day as we're patching in some new things between multiple different versions of software. So it's available. In some cases, it might be interesting to use, but it's not as well supported, and we don't recommend it in general. This blue kind of build is what we call a candidate build. That's something that we've finished the software development work on, we consider it done, and now we're in the middle of testing it. So there's actually a fairly extensive testing period that goes on when we finish a software build. So there's not only unit tests that happen all the time as we're working, but at the end of a build, there's actually a much more extensive set of tests that we go through as well. We have a number of science example cases that we will process all the way through from beginning to end and ask, does everything look good? Does the science look like we'd expect, etc., before we actually formally move ahead with this. These candidate builds are a lot easier to use. For somebody who wants to keep up to date with the latest recommended thing, that's probably a good way to go. And finally, there's the operational builds. This is what I've got in green. That's our default recommendation. This is something that we've finished the development, we're happy with it, and that's what we're in the middle of running internally to produce all the data products you get out of MAST. This is the most well-tested, the most well-supported, and the generic recommendation, but it's not going to be the bleeding edge. If you want the very latest things, you might be interested in one of these other two instead. And then finally, there's the archived versions, things that used to be our operational builds, but now getting old enough that they're not the versions we run anymore. This gives you an idea about roughly where we are right now. This table is actually out of date as of 2 days ago, so I need to update it. In the sense, we're still working on developing build 11.3, but operations actually just switched over from 11.1 to 11.2 earlier this week. So our candidate had finished testing, now it's actually in operations, and soon we'll be moving on to the next stage of development. This table, of course, updates regularly, and I put a link here to JDocs where you can find out what the latest table is at any given time. And it tells you what the mapping is between what I'm calling the pipeline build, or the high-level version number, the JWST software number associated with it, the CRDS context number, this is the version of the reference files that's associated with it, and roughly what the timeline has been. So if you're interested in a look forward about where we have been and where we're going, essentially we're here. We just got 11.2 installed, as I said. We're working on 11.3. Soon we'll be moving over into developing what we're calling Pipeline 12.0, and there's a constant chain of builds about every 3 or 4 months or so over any given year. So taking a step back, why do you want to run the pipeline yourself? And I just told you that we install a given version of the pipeline at Space Telescope. We run it on our own systems. We provide all of the data in MAST so that you can download it. So why would you actually want to download and run the pipeline yourself? And the reason why is because the pipeline does the best that it can do with default settings for all of the different instruments and all of the different science cases that we've got. As I mentioned earlier, that's got to be reasonable defaults for everything from Jupiter to cosmology and exoplanets to nearby galaxies. Those default settings will not be ideal for everybody. And so there's always going to be improvements that you can make to the data quality for specific science cases by using non-default settings. And that requires scientific judgment, your scientific judgment about what does my data need in order to help make it better. And that's where we try and allow the pipeline to provide the tools that you need to make those improvements, but it's going to be your judgment as to whether or not those improvements actually help your data or not. A couple things to keep in mind when you're reducing your own data, namely it takes up a lot of space. So keep in mind you'll need a number of gigabytes available on your machine to process data. Some reference files, for instance, are 6 gigabytes each. We're working on seeing if we can cut that down in future, but the raw data itself that you're working with, if you're working with multiple near-cam observations, for instance, many different cameras reading out for a long ramp for 15 minutes, the raw data files themselves can often be 10 gigabytes or more. So free up some disk space before you start working with web data so that you don't run out. If you want to start working with web data, then you'll want to start with actually downloading the data yourself. There's a number of ways that you can go about doing it. I provided a link up here to the top to an overview of these, but the two sort of easiest ways you're going to be interested in doing is using either this thing called the MAST portals. This is the main MAST interface you might be familiar with, which is general purpose and serves multiple different missions and allows you to preview what the data itself looks like. At least for things like imaging, then you can look at a field and say, oh, yep, that's my field. There's something more recent as well, a JWST data specific mission search, which only searches web data, but can sometimes be rather easier to navigate to the kinds of files that you're interested in. And there's a variety of other methods as well. You can do programmatic methods via Astro Query and Python, so you don't need to click through everything. But a key thing to keep in mind is you can download only the products you're interested in. You can only download the final data products if you say, I think the default calibration is fine for my science. I'm just going to download the mosaics and the data cubes and go from there. Or you can download the intermediate files. If you think you want to rerun the end stage pipeline, download the cal files. If you want to just rerun higher stages, download rates. If you want to start at the beginning of the pipeline, download the uncal files. It's tailored so there's lots of intermediate products, and you can choose where you want to start your own processing. So we're just about up, well, probably be a good time for a break right now, but just a couple more slides first. A reference slide, again, it's got a lot of information on it. I don't anticipate anybody's going to type it in right now, but you can look back at it later in terms of how to install the pipeline. The main thing you need is a Python install. We often recommend Anaconda Python because then you can set up special environments for your particular usage. And installation itself is actually really straightforward. Once you have a Python setup going, you just create a new Conda environment for it, and then you pip install the version of JWST that you're interested in. There's some other packages you might need to install as well. For instance, if you want to run Jupyter Notebooks, you will need to install the Jupyter client. Keep in mind that things won't work well if you try to open a Jupyter Notebook without installing Jupyter, so that's an important part of this. And then finally, there's some notes at the bottom that are optional. You don't need to do it if you're running a pipeline notebook. So if you want to do things outside of the notebooks, you need to do some configuration to where to find the reference files. Notebooks take care of that for you, though, which is why they're one great place to start with working with the pipeline. In terms of running the pipeline, you can either run it from the command line, again, if you've set things up to find reference files, or you can run it from within in Python itself as functions. But again, the version we recommend is using Jupyter Notebooks, which is what we'll be moving on to in a moment.